It's very interesting. Can you tell a bit, well, like, what does it mean, smart contract coverage, and how it works,
Yeah.
like on the back end, behind the scenes? Like, what does it mean for users and for the people who cover it?
Yeah. So
the insurance.
Yep. So the smart contract coverage, somewhat, some would call it insurance. There's different regulatory meanings of different words, so we try to be careful about what we call things. But the basic idea is that Sherlock is actually a B2B one. So let's say you are Uniswap and you build new smart contracts, and your users are going to be using those smart contracts and kind of LPing, putting their funds into it. The funds are going to sit there, and they're basically at risk when they're sitting there in those Uniswap smart contracts. And Uniswap might say, okay, we want to go out and buy $100 million coverage policy. So if we get hacked, this coverage policy will pay us $100 million, and we can use that $100 million to reimburse our users effectively. And for that privilege, Uniswap will pay like a monthly fee. I mean, everyone is kind of familiar with paying car insurance or paying, different
house
types of insurance in their daily lives, house insurance, travel insurance. It's a very similar thing where it's like, okay, you make a small payment semi-regularly, and then if the really bad thing happens, if the trigger happens, then a big payout comes in the other direction. Like a big payout comes to you. So that's the basic idea of smart contract coverage is, all right, we're going to pay these premiums and do that monthly or whatever. And if a hack happens on our smart contracts, which it's hard to ever 100% know that a hack isn't going to happen. If a hack happens on our smart contracts, then Sherlock or someone else is going to pay us back, a large sum of money so that whoever lost money in that hack can get reimbursed. That's kind of the basic idea. There's a whole on-chain implementation that Sherlock has that I can kind of go through.
Yeah, that was my next question. How do you enforce it on-chain, or maybe it's being handled off-chain?
Yeah, so no, it's 100% on-chain. The hardest part, which was a huge point of controversy for many years. Yep.
How do you know that the contract got hacked? Basically, you check his balance, his token balance and ETH balance, and see that basically it was decreased. What if it's just someone just removed liquidity? There should be some kind of like observation or like to see if like you cannot really automatically detect, or maybe you can. I don't know if it's a hack or not, right?
So this was a huge point of contention in the early years of Sherlock. A lot of investors didn't like Sherlock because there's almost like a religious debate of, can you use code triggers to know if a smart contract got hacked or not? Like, is there a way to detect in code this smart contract got hacked? It wasn't something else. It wasn't a user withdrawing their deposit. It wasn't some, functionality that occurs every so often. And Sherlock actually took the side of, you cannot know in code that a hack occurred, like with 100% accuracy. And the reason for that is, as the smart contracts get complex enough, imagine some of these derivatives protocols, some of these different things, the triggers have to become more complex. And eventually the triggers essentially have to be so complex that they mimic a lot of the functionality of the protocol itself. Like they have to know, okay, in this situation, this isn't a hack because this is just a liquidation, or this is this thing happening because this user, fell below this threshold. And so the triggers have to be so complex that they start to mirror the code of the protocol itself. And once you start doing that, then if there are bad assumptions or there are smart contract bugs in the protocol, then you're mirroring those into the trigger itself at a certain point. And so that's one of the reasons why we didn't think it was possible. Another one is just because, using code to detect bugs in code is just a really hard thing philosophically. Like the code is not smart enough. Like the code only knows what that code is doing. It doesn't know what it's supposed to do. Like it has no ability to understand intention.
It's like static analysis. It will never cover everything. I mean, I don't know if it's not exactly like static analysis, but it's like similar. You cannot really write code that will 100% detect all the bugs. you still need like a human observation or something like fuzz testing? Or
yeah, you can have different scenarios. You can have different pieces of coverage where you're like, okay, if this goes wrong this way, then we'll know. Or I guess it's really saying if this test doesn't pass, then we'll know that something might be wrong. So that's a big part of it. And then there's this other side of doing it programmatically, which is, okay, you're going to have, this was a kind of an early one that I think a different protocol used. They're like, okay, you're going to have Compound, you're going to have CUSDC. Like you put USDC into Compound, you get CUSDC. If your CUSDC goes below 95 cents, like if Oracle, I think they were using an Oracle at that point. I forgot if it was Chainlink or if it was Uniswap. But if the Oracle value of your CUSDC goes below 95 cents, then you get a payout. And that actually works. Like that is pretty, it makes a lot of sense. Anytime a hack happens that's bad enough, it's going to drop below 95 cents. Like the value of CUSDC is going to drop below 95 cents. And so that works really well. The problem is if you're having that trigger, then you're also saying every non-hack scenario that causes it to go below 95 cents, you're also paying for that. And in Compound, there are lots of non-hack scenarios like that can cause that are just economic things occurring. Like somebody could, bad debt can accrue. These things that are normal in a lending protocol can actually cause the value of your collateral to go below 95 cents. If the liquidations don't happen fast enough, then your collateral can easily go below 95 cents. And so then the insurance or the smart contract coverage that is paying for that 95 cent kind of trigger policy, you basically have to pay it all of your yield, because the only reason you're earning yield is because you're taking some kind of risk somewhere. And that 95 cent trigger is taking away all of the risk scenarios that could cause it to go below 95 cents. And so you're not really doing anything in that case, because that person is going to make zero yield. They have to pay you all of the yield, because you are taking on every risky scenario that could cause it to go below 95 cents instead of just the smart contract hack scenario. So anyways, that was a way too long answer about why trigger-based smart contract coverage is not super realistic. But I think a lot of the coverage protocols that were doing that back in the day, they're either not around now or they've switched to the unfortunate necessary model that Sherlock also uses, which is human-based on-chain triggers. And so that's the UMA Optimistic Oracle. If you're familiar with that, that's what Sherlock uses. There's also Claros Court, which is a different implementation, which, we don't like as much as the UMA Optimistic Oracle, but I think they're trying to do good things there as well. And Sherlock has its own, it's called a claims committee that some top kind of security experts are on, and they can make a decision pretty quickly and have the right, context, hopefully to understand the exploit. So it's human-based triggers, but it is fully on-chain, which is cool. So there's no off-chain component.
It's a very good trade-off or workaround, I believe. Yeah, it makes sense. Like that this is like the solution that you had to come with, because it's not really possible to do it 100% on-chain automated. It doesn't seems like feasible, at least not these days, maybe in the future. Yeah, indeed.
Yeah,